This is part 2 of the Science Fusion presentation on the elevated mixed layer and its association with severe convective storms in the northeastern U.S. In part 2, we'll be examining a case study and discussing real-time operational tools. To better understand the role of the EML in a northeastern U.S. severe weather event, it is instructive to look at a case study. This case is from the 15th of May 2018 and featured an SPC moderate risk, which was upgraded from an enhanced risk with the 1630Z Day 1 Outlook issuance. On the right, you can see that there was a large concentration of severe weather reports across eastern Pennsylvania, southeastern New York, into southern New England on this day. This included 12 tornadoes of EF0 to EF2 intensity, 12 significant hail reports, and 2 measured significant wind reports. The elevated mixed layer in question for this event can be seen in the Pittsburgh observed sounding at 12Z that morning, with a well-defined zone of steep mid-level lapse rates. The EML had been eroding gradually during the prior 24 to 48 hours, as we will see evidence of in the slides that follow. With that said, there is still a 150 millibar layer with a lapse rate of 8.7 degrees Celsius per kilometer, which will help bolster buoyant accelerations with developing convection. The layer is also relatively dry, which will play a role in enhancing thunderstorm downdrafts once they develop. Note that the EML is located within relatively strong mid-level winds with west-southwesterly flow of 45 to 50 knots between 700 and 500 millibars. The EML was identified by the SPC Outlook forecaster and included in the Day 1 Outlook discussion. The combination of the EML, strong surface heating, and strong deep layer shear led to a 1630Z upgrade to a moderate risk of severe storms across northeastern PA, southeastern New York, northern New Jersey, and into southern New England. The 500 millibar analysis at 0Z on the 15th of May, roughly 18 hours before the event unfolded, featured a mid-level anticyclone and clockwise rotating winds across the Tennessee Valley. Between this area of high pressure and the trough across the northern Great Lakes and James Bay, there was a broad region of enhanced mid-level west-southwesterly flow extending from the Central Plains east-northeastward across the mid-Mississippi Valley, Great Lakes, and Ohio Valley regions into the northeast. By 12Z, this band of enhanced mid-level flow strengthened further as the ridge over the Tennessee Valley weakened and the curvature of the flow became slightly cyclonic from the eastern Great Lakes into the northeast. 500 millibar wind speeds of 50 to 55 knots are evident at 12Z across Ohio, Pennsylvania, and the southern tier of New York. Comparing the two charts, 12-hour height falls can be seen across Ohio, Pennsylvania, and the eastern Great Lakes region. By 12Z, 500 millibar temperatures had also cooled to minus 14 Celsius at Pittsburgh and Buffalo, ahead of a shortwave trough moving eastward through the central Great Lakes region. Looking at GOES satellite imagery, we can see a band of very dry air in the 7.3 micron water vapor imagery at 1227Z, extending from the Tennessee Valley northeastward into Pennsylvania and New Jersey. This low-level water vapor band, channel 10, can best observe the 700 to 500 millibar layer of the atmosphere and can be quite useful for identifying and tracking EMLs, which are associated with dry mid-tropospheric conditions. Refer to Gitro et al. From 2019 for more details on tracking the EML using satellite-based tools. On the water vapor image, I've overlaid the GFS initial hour 700 to 500 millibar lapse rates. While the model is indicating lapse rates slightly lower than sounding observed values, the viewer can still get the sense that there is a band of steep 700 to 500 millibar lapse rates coincident with this zone of dry air in the water vapor imagery. The visible satellite imagery from 12 to 13Z on the right indicates a wide area of cloud-free conditions conducive for strong daytime surface heating. Upstream convective storms are already developing in the Binghamton area and also across northern Ohio, associated with increasing cyclonic flow. Based on surface obs, 2-meter dew points in the low to mid-60s are already in place. An increasing low-level southerly flow will result in a gradual increase in surface dew points throughout the day into the moderate risk area. At the surface, a modest surface low and trailing cold front was analyzed across southwestern New York and western Pennsylvania at 15Z, which translated eastward into the early afternoon hours. South and east of the cold front, a prefrontal trough developed. Near and east of the prefrontal trough, with the strong insulational heating, surface temperatures by 18Z had warmed into the mid to upper 80s, with surface dew points in the mid to upper 60s. This resulted in very steep low-level lapse rates as well, favorable for surface-based convective initiation. Convective inhibition quickly eroded, and surface-based CAPE values reached or exceeded 3,000 joules per kilogram over portions of the moderate risk area by 18Z. This, combined with surface to 6 kilometer bulk shear of 45 to 60 knots, produced an extremely favorable environment for widespread severe convective storms. Using the high-split model, we can run 72-hour backward trajectories from Pittsburgh to see where the mid-level air mass and EML originated from. When we do this, we see that the 5,000-meter trajectory originated from the Southern Rockies 3 days prior. This is consistent with the 700 millibar analysis at Wright and general flow regime. There was a deep trough across the Great Basin in southwestern U.S., and this initially helped eject the EML plume northeastward across the southern plains and into the mid-Mississippi Valley area. Another thing you'll notice in the trajectory analysis at left is the presence of these anticyclonic loops, which were made by air parcels over the lower Ohio and Tennessee Valley areas. This is pretty common to see in cases where the EML makes it all the way to the northeast, because that anticyclone and associated subsidence is important to the long-range transport of the EML. The period from roughly 18Z on May 13th through 0Z on May 15th is also a time when there is a subsidence noted in the parcel trajectories in the bottom portion of the image at the left. So the anticyclonic flow and subsidence is helping to maintain the EML for a relatively long period of time before becoming entrained in the faster airstream as the flow becomes cyclonic towards the daylight hours on May 15th. Again, that's a common feature in the synoptic climatology for these types of northeast EML events. And here we can loop the 700 millibar analysis over roughly a 2.5 day period. In the orange shading, we can see the 7 to 500 millibar lapse rates of 8C per kilometer or greater and how it moves and evolves with time. The green shaded areas represent 700 millibar relative humidity of 70% or greater, so usually these two features will remain distinct from each other given the thermodynamic properties of the EML itself. So if we loop this, you can see the pocket of steep lapse rates that gets entrained into the anticyclone and stagnates over the Tennessee Valley area while slowly eroding. Towards the end of the loop, you can see lapse rates of 7.5 to 8 degrees C per kilometer get advected northeastward in advance of the trough approaching from the Great Lakes. Again, model-based lapse rates are usually somewhat underdone, so anything over 7C per kilometer or so is generally worth paying attention to in a model-based analysis. And again, the SPC mesoanalysis is based on a RAP first guess field. And even though the EML is gradually losing its properties through time, the pocket of steep lapse rates that survived into Pennsylvania and southeastern New York was important for enhancing the severe storm environment on the 15th and contributed to very intense convective storms. And for added context, we can examine observed soundings along the path of the trajectory to see the presence and evolution of the elevated mix layer. At 0Z on May 13th, the trajectory was closest to the Dodge City sounding location, which revealed a deep EML extending from roughly 800 to 500 millibars. Lapse rates are near dry adiabatic values, especially in the upper half of the EML annotated on the sounding. And you can see the 40-knot southwest flow in this layer, which is advecting that EML plume off to the east-northeast. By 0Z on May 14th, the trajectory is closest to the Nashville, Tennessee sounding location. This is near where the anticyclonic loops were noted, and the sounding shows the EML from roughly 750 to 500 millibars, and a strong capping inversion just below. The winds are much lighter here, and from the northwest, part of the clockwise rotation around 700 millibar high pressure noted in this general area on May 14th. So this is starting a period of subsidence, which will help to maintain the EML and bolster the capping inversion through downward stretching effects. And finally, at 12Z on May 15th, the EML has reached Pittsburgh. You can see that the EML is shallower and has eroded below 700 millibars, and the capping inversion is also shallower and weaker. This is likely a function of vertical motion and vertical stretching, which is now acting on the environment at this time near the base of the EML. The mid-level wind speeds are much faster now as well, as the EML is caught up in the developing cyclonic flow in advance of the shortwave trough. Winds are 45 to 50 knots in the 700 to 500 millibar layer as we lead into the severe weather event that commenced several hours later. Here's a visible satellite loop from 16 through 19Z on May 15th, showing rapidly developing convective storms across Pennsylvania and southeastern New York. In advance of the deeper convection, the towering cumulus field indicates where the boundary layer is generally favorable for surface-based convective development, and these storms increase in coverage and intensity as they move eastward in advance of the cold front and prefrontal trough into the axis of maximum surface-based instability. And you can readily see the intensity of these convective storms from the Binghamton radar as they marched across northeastern Pennsylvania and southeastern New York between 1814Z and 1909Z that afternoon. We see a mix of discrete supercellular convection to the north and east with evidence of splitting supercell thunderstorms. And then back across Pennsylvania, we generally have more of a linear storm mode that has developed with small-scale bow echoes, associated weak echo channels, and a broad trailing stratiform region. There are numerous severe thunderstorm and tornado warnings out during this time period, and we see some very intense reflectivity cores and sharp reflectivity gradients with much of the convection, which is strongly indicative of the intense updrafts and strong organization of the convective activity on this particular day. We'll briefly take a look at a couple of these thunderstorms next. A vertical reflectivity cross-section through this bowing segment near the northern end of the convective line in Susquehanna and Wayne County, Pennsylvania, featured 54 dBz echoes up to 41,000 feet above radar level. Looking at a base velocity cross-section for the same storm, we see evidence of a mid-level radial convergence or a Mark signature between 10 and 20,000 feet, an intense storm top divergence of 127 knots in the 40 to 50,000 foot range. So some very intense features on radar with this storm. This was the radar data associated with a weak tornado just past 19Z over eastern Wayne County, Pennsylvania. A brief spin-up occurred along the line of convection with storm relative velocity, gate-to-gate shear reaching 54 knots outbound and 27 knots inbound. This yields 40 knots of rotational velocity, roughly 45 nautical miles from the RDA, which is in the range of a moderate mesocyclone. This period of time shown was associated with a drop in correlation coefficient and a tornadic debris signature in the correlation coefficient data, with max outbound base velocities of 72 knots just over 3,000 feet above radar level. There's some evidence of a hook echo in the base reflectivity data as well. A storm survey confirmed an EF1 tornado, with this storm in addition to a violent downburst. And lastly, this is one of the supercell thunderstorms located further northeast in Sullivan County, New York at 1830Z. This storm had a maximum estimated hail size of 4.5 inches and an obvious 3-body scatter spike. A broad 65 dBz core extended up to 33,000 feet above ground level. There weren't any hail reports in this immediate area, but downstream in the community of Livingston Manor, they reported 2-inch diameter hail 20 minutes after this image at 1850Z. There are a couple of ways to monitor and track the EML on the Storm Prediction Center mesoanalysis page. There is a traditional plot of mid-level lapse rates defined by the 700 to 500 millibar layer, as shown at right. Because the steepest mid-level lapse rates don't necessarily conform to the mandatory pressure levels, another graphic was added which indicates the maximum environmental lapse rate in the 2 to 6 kilometer AGL layer. This is based on a procedure that looks for the maximum lapse rate in a 2 kilometer deep layer within the bounds of 2 to 6 kilometers AGL. This max 2 to 6 kilometer lapse rate product will generally show higher lapse rates than its traditional counterpart and can be a little better at resolving the EML on days when it is somewhat shallower or offset from the 700 to 500 millibar layer. When looking for elevated mixed layers, it is important to have forecast tools to help examine and visualize steep mid-level lapse rates. While EMLs aren't tied to mandatory pressure levels, they can usually be identified in the central and eastern United States by examining 700 to 500 millibar lapse rates. You generally want to see at least 7 degrees C per kilometer or greater as a lapse rate as a starting point to get your attention. Sometimes this can happen beneath cold core upper lows, but by tracking the origin of the steep lapse rates, you can generally distinguish between steep lapse rates reflecting elevated mix layers and steep lapse rates caused by other processes. In particular, you'll want to look for anomalously high values of 700 to 500 millibar lapse rates upstream or plumes ejecting from the Intermountain West. Based on the synoptic composite studies, you'll also want to look for a west coast mid-level trough to help eject the EML plume and a strong ridge over the Tennessee Valley, which generally helps to preserve the EML plume eastward. In the hours preceding a severe event, what's left of the EML will generally get entrained out ahead of a low amplitude mid-level shortwave trough approaching from the Great Lakes. And be aware that in deterministic and ensemble model forecasts, lapse rates are generally less than what the observed soundings will show. Be aware of this and any convective feedback which might not be real and could be lowering lapse rates below what is actually being observed in the sounding data. This concludes the presentation on the elevated mix layer and its association with northeastern U.S. severe weather. If you have any questions, feel free to send me an email. And in the meantime, happy severe weather forecasting to all.